Welcome to Sleepy Science. Tonight, we begin a quiet journey through one of the universe's greatest mysteries, its expansion. For more than a century, astronomers have watched galaxies drift away from us, as though space itself were stretching. But this motion raises one profound question. Will it go on forever? Or will it one day stop? For most of human history, the idea that the universe could expand was unimaginable. The night sky appeared eternal, the stars seemingly fixed in place. Philosophers and astronomers assumed that the cosmos was static, neither growing nor shrinking. Even Albert Einstein, when he developed his general theory of relativity in 1915, believed the universe must be balanced, unchanging through time. His equations, however, predicted something different. Einstein's mathematics showed that gravity alone would cause the universe to collapse inward unless there was something to counteract it. To preserve the idea of a static cosmos, he introduced a mathematical term called the cosmological constant, a kind of anti-gravity that would hold space in place. He thought of it as a necessary correction, but it would later become one of the most important ideas in modern cosmology. In 1929, American astronomer Edwin Hubble made a discovery that changed everything. Using the 100-inch telescope at Mount Wilson Observatory, he measured the distances and light from distant galaxies. He noticed that their light was redshifted, stretched toward longer wavelengths, which meant they were moving away from us. Moreover, the farther away a galaxy was, the faster it receded. This relationship, now known as Hubble's law, revealed that the universe was not static at all. It was expanding. Every point in space was moving away from every other point, not because galaxies were flying through space, but because space itself was stretching. The universe was growing, and every galaxy was carried along with that growth. If the universe is expanding today, it must have been smaller in the past. Rewinding that expansion leads inevitably to a beginning, a time when everything was compressed into a single, dense state. That realization gave birth to the Big Bang Theory, which describes how space, time, and energy all emerged from a single point about 13.8 billion years ago. But expansion does not necessarily mean infinity. It could, in theory, slow down, stop, or even reverse, depending on how much matter and energy the universe contains. Gravity works to pull things together, while the momentum of the Big Bang pushes them apart. The outcome depends on which force dominates. In the early universe, matter and radiation were dense enough to slow expansion, but not stop it. Over billions of years, as the universe thinned, the pull of gravity weakened. Astronomers expected that expansion would gradually decelerate, like a stone thrown upward that slows before falling back. Then came a surprise. In the late 1990s, two independent teams studying distant type Ia supernovae, exploding stars used as cosmic distance markers, found that the expansion was not slowing down at all. It was accelerating. Something unseen was pushing the universe outward, faster and faster. That discovery reintroduced Einstein's forgotten term, the cosmological constant, now understood as a possible form of dark energy. Whatever it is, it makes up about 70% of the total energy in the cosmos. And it dictates how the universe will evolve from now on. The mystery, then, is not whether the universe is expanding. We know it is. The mystery is whether that expansion will ever stop, or if it will continue forever, driven by forces we still don't fully understand. In the next part, we'll explore how astronomers measure that expansion, how redshift, light, and distance together reveal the universe's dynamic motion through space and time. When we talk about the expansion of the universe, it's easy to imagine galaxies rushing outward through empty space, as though they were pieces of shrapnel from an explosion. But that picture isn't quite right. Galaxies are not moving through space. Instead, space itself is stretching, and the galaxies are being carried along with it. To understand this subtle motion, scientists had to learn how to measure something that cannot be seen directly: the change in the very fabric of space. The most powerful clue comes from light. When light travels across the universe, it behaves like a messenger carrying information from the past. As space expands, the waves of light traveling through it also stretch. This stretching increases their wavelength, shifting their color toward the red end of the spectrum, a phenomenon called redshift. The greater the redshift, the faster the source is moving away. By comparing the redshift of a galaxy's light with its distance, astronomers can measure how quickly the universe is expanding. This relationship is described by the Hubble constant, a number that represents how much the speed of recession increases per unit of distance. For every megaparsec, about 3.26 million light-years, galaxies move away by roughly 70 kilometers per second, though the exact value is still debated. Determining that constant precisely has become one of modern astronomy's biggest challenges. There are two main ways to measure it, and they don't yet agree. The first method uses standard candles, objects whose brightness we know well, such as Cepheid variable stars and type Ia supernovae. By comparing their true brightness to their observed brightness, astronomers can calculate how far away they are. Their redshift then tells how fast the universe has stretched since their light began its journey. The second method comes from studying the cosmic microwave background, CM, the afterglow of the Big Bang. By mapping tiny variations in that ancient light, missions like WabaMap have revealed the universe's composition, shape, and age. These measurements allow scientists to calculate what the expansion rate should be today if the physics of the early universe has remained the same. The two results differ slightly, a puzzle known as the Hubble tension. The local measurements using nearby galaxies suggest a slightly faster expansion than the early universe predictions based on the CMB. Some scientists suspect this could point to new physics, perhaps changes in dark energy over time, or interactions we don't yet understand. Despite this tension, both methods agree on the essential truth. The universe is expanding, and it has been for nearly 14 billion years. The light from distant galaxies tells the story with perfect consistency. The farther back we look, the faster things were moving apart. This cosmic expansion is not something we can feel on human scales. Gravity holds together everything local: the Earth, the solar system, even our entire galaxy. The expansion of space only becomes noticeable across the immense voids between galaxy clusters, where gravity is weak enough for space itself to stretch freely. By studying how the rate of expansion changes over time, scientists can learn about the balance of forces in the universe. In its first few billion years, matter dominated, and gravity slowed the expansion. Later, dark energy took over, accelerating it. By measuring this transition from deceleration to acceleration, we can trace the history of cosmic expansion and predict what comes next. Every photon that reaches our telescopes carries a timestamp of this growth. When we observe a galaxy whose light has traveled for 10 billion years, we are seeing the universe when it was young and more compact. We can literally watch the cosmos expand by comparing light from near and far. The more precisely we measure this expansion, the closer we get to answering the ultimate question: will it ever stop? Or has dark energy locked the universe into an eternal stretch toward emptiness? In the next part, we'll dive deeper into the forces that shape expansion, the delicate competition between gravity, matter, and dark energy that determines whether the cosmos will slow, freeze, or accelerate without end. Every movement in the universe, from the orbit of planets to the drift of galaxies, is shaped by a balance of forces. The expansion of the cosmos itself follows this same rule. For most of cosmic history, two great influences have fought for dominance: gravity, which tries to pull everything together, and the momentum of expansion, which drives galaxies apart. Gravity is familiar to us. It's the same force that keeps the moon circling the Earth and holds the planets around the sun. But on the largest scales, gravity acts on everything with mass or energy. Every galaxy, every atom, even light itself contributes to the total gravitational pull of the universe. In the early universe, when matter was extremely dense, gravity's influence was immense. It slowed expansion, trying to draw space back in upon itself. If the universe had contained enough matter, gravity could have overcome the outward motion and caused everything to collapse again, a fate known as the Big Crunch. In that scenario, galaxies would eventually stop receding, then begin to move inward, leading to a universe that ends much as it began, in a state of infinite density and heat. For much of the 20th century, scientists debated this question. Would expansion go on forever, or would it one day reverse? The answer depended on the universe's critical density, the exact amount of matter and energy needed for gravity to perfectly balance expansion. If the total density were higher than this critical value, gravity would eventually stop the expansion. If lower, expansion would continue forever. To find that balance, astronomers needed to know how much matter the universe actually contains. Observations revealed that visible matter, the stars, planets, and gas we can see, accounts for only a tiny fraction of what's needed. The galaxies alone did not have enough mass to stop expansion, but their motion hinted at something more. When scientists studied the way galaxies rotate, they discovered that stars near the edges were moving far faster than they should be based on visible mass alone. The same pattern appeared in galaxy clusters, where the outer galaxies moved as though pulled by unseen gravity. This led to the concept of dark matter, an invisible form of matter that interacts through gravity, but not with light. Dark matter makes up about 27% of the total energy content of the universe, compared to only about 5% for ordinary matter. Even with this addition, though, the total density still seemed too low to halt expansion completely. The universe appeared to be open, destined to keep expanding forever, though perhaps more slowly over time. Then came one of the most surprising discoveries in all of science. In the late 1990s, teams studying distant type Ia supernovae expected to see evidence that expansion was slowing. Instead, they found the opposite. The universe's expansion was accelerating, pushed by a mysterious force that overcomes gravity on the largest scales. This force, now called dark energy, makes up roughly 68% of the total energy of the cosmos. It acts like a uniform pressure built into space itself, causing the rate of expansion to increase with time. Unlike gravity, which weakens with distance, dark energy grows stronger as space expands, because it is linked to the volume of space itself. If dark energy remains constant, the universe will continue accelerating indefinitely. If it changes over time, other futures become possible. But one thing is clear: at the current rate, gravity will never be strong enough to reverse expansion. The cosmos has passed a threshold, the point where matter's pull is too weak to slow the outward flow. The delicate balance between gravity and dark energy defines everything. On smaller scales, within galaxies and clusters, gravity still dominates, binding matter together. On the vast scales between clusters, dark energy wins, stretching the fabric of space faster than gravity can resist. The universe, therefore, is both bound and unbound, stable and expanding at the same time. This interplay tells us that the universe will not stop expanding anytime soon. But could that ever change? Could dark energy weaken, fade, or reverse its effect? To answer that, we must understand what dark energy really is, and that remains one of the greatest mysteries in physics. In the next part, we'll explore the nature of dark energy, what we know about it, and how it shapes the future of cosmic expansion, perhaps forever. When astronomers discovered that the universe's expansion was speeding up instead of slowing down, It marked a turning point in our understanding of everything. Something unseen was overpowering gravity on the largest scales, pushing galaxies away faster and faster as time passed. This mysterious influence was named dark energy, and though it fills roughly 2/3 of the entire cosmos, we still know almost nothing about what it actually is. Dark energy does not emit light, it does not absorb light, and it does not clump together like ordinary matter. It seems to be a property of space itself, a constant energy density that remains the same even as the universe expands. The more space there is, the more dark energy there is. That simple fact explains why cosmic expansion accelerates. As space stretches, the amount of dark energy increases in proportion, and its repulsive effect becomes stronger. The simplest explanation for dark energy is the cosmological constant, a term that Albert Einstein introduced into his equations of general relativity in 1917. At the time, he wanted a static universe, so he added this term to balance gravity. When Hubble later discovered that the universe was expanding, Einstein supposedly called the cosmological constant his greatest blunder. Yet decades later, it turned out he might have been right all along. The constant could be real, not to stop the universe from collapsing, but to explain why it accelerates. If dark energy is indeed a cosmological constant, it means that empty space is not truly empty. Quantum physics predicts that even in a vacuum, particles and antiparticles are constantly flickering into existence and vanishing again. These fluctuations give the vacuum a small amount of energy, vacuum energy, that could act as the source of dark energy. Other explanations suggest that dark energy might not be constant at all. Some theories propose a dynamic field called quintessence, which changes slowly over time and space. Unlike a cosmological constant, quintessence could grow weaker or stronger depending on its interaction with matter and energy. If it changes significantly in the far future, it could alter the fate of the universe, possibly halting the expansion or even reversing it. Still, all evidence so far supports the idea that dark energy behaves like a constant force. Observations of supernovae, the cosmic microwave background, and large-scale galaxy surveys all show that acceleration has been consistent for billions of years. If it continues unchanged, the expansion will never stop. Instead, it will gradually separate galaxies until most are forever isolated, invisible to one another. What makes dark energy so difficult to study is that its effects are subtle and act only across vast distances. It does not influence the motion of planets or stars within galaxies. It only becomes significant when we look at scales of hundreds of millions of light years, where it determines how the universe evolves as a whole. Even though we cannot see dark energy directly, its fingerprints are everywhere. The distribution of galaxies, the shape of the cosmic web, the tiny ripples in the background radiation, all of these patterns carry its signature. Astronomers continue to map the sky in greater detail, hoping to detect even the slightest hint of change in the acceleration rate. If dark energy truly is constant, the universe will keep expanding faster and faster, forever. If it changes, the story could end differently. In some models, a decaying dark energy field could one day weaken enough for gravity to slow expansion, or it could strengthen so much that it tears space itself apart. The destiny of the cosmos depends entirely on this invisible force. It began as a small term in Einstein's equations, but it has become the defining feature of the modern universe. The search to understand it is one of the deepest and most challenging quests in physics, not just because it tells us about the future of the universe, but because it might reveal the fundamental nature of reality itself. In the next part, we'll see how scientists test these ideas, how telescopes and satellites measure dark energy's influence over billions of years, and what those measurements tell us about when, or if, the universe might ever stop expanding. After the discovery that the universe's expansion is accelerating, astronomers faced a new challenge: to observe this mysterious force directly. Since dark energy cannot be seen or touched, its presence can only be inferred from the motion of galaxies, the brightness of distant supernovae, and the geometry of space itself. By carefully measuring how fast the universe has expanded at different points in its history, scientists can trace the strength of dark energy and predict how it may behave in the future. The first major evidence came from the Type Ia supernova surveys of the 1990s. These special supernovae act like cosmic yardsticks because they explode with nearly identical brightness. By comparing how bright they appear from Earth, astronomers can determine their distance. When their light is also redshifted, stretched by cosmic expansion, scientists can calculate how fast the universe was growing when the explosion occurred. By gathering data from dozens of supernovae at different distances, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, discovered that galaxies billions of light years away were moving apart faster than expected. That acceleration could only be explained if an unknown form of energy was pushing space outward. Since then, newer telescopes and missions have expanded this work. Projects like the Dark Energy Survey, the Baryon Oscillation Spectroscopic Survey, BOSS, and the Euclid Space Telescope have mapped millions of galaxies, measuring the subtle ripples in their distribution. These ripples, known as baryon acoustic oscillations, are the leftover imprints of sound waves from the early universe. Their spacing provides a standard ruler for measuring cosmic expansion over billions of years. Observations of the cosmic microwave background, the faint glow left over from the Big Bang, also reveal how dark energy shapes the universe. By analyzing the small temperature variations in that radiation, satellites like DEMMAP and Planck have shown that space is remarkably flat, meaning its total energy density is very close to the critical value. The missing energy needed to reach that balance must come from dark energy itself. Another way scientists study dark energy is through gravitational lensing, the bending of light by massive objects. As light from distant galaxies passes through clusters of galaxies on its way to us, the paths of those light rays curve slightly. By measuring how much they bend, astronomers can map the distribution of dark matter and see how space has stretched between those objects. The results confirm that the universe's expansion rate has increased over time. All these methods, supernovae, baryon oscillations, lensing, and the cosmic background, point to the same conclusion. Dark energy behaves like a constant pressure that pervades all of space. If that remains true, the universe will never stop expanding. The distance between galaxies will continue to grow forever, and the night sky will slowly empty as more galaxies fade beyond the cosmic horizon. Still, scientists continue to look for signs of change. Could dark energy vary over time? Could it weaken, allowing gravity to slow expansion? Or could it grow stronger, leading to a catastrophic big rip, where even atoms are torn apart? These are not philosophical questions, but physical ones, and the data we collect in the coming decades may reveal the answer. In essence, we are watching the future unfold in slow motion. Every photon that reaches Earth carries a record of how fast space was expanding when it left its source. By piecing together these signals, astronomers can reconstruct the universe's entire timeline, from the first light to the possible end of all things. Dark energy defines the destiny of the cosmos. Yet for now, we only know how it behaves, not what it is. It could be a property of space-time, a field that changes, or an effect of dimensions beyond our perception. Whatever it is, it will determine whether the universe coasts into eternal expansion or finds a way, however subtle, to pause. In the next part, we'll explore the possible futures of cosmic expansion. What will happen to galaxies, stars, and space itself under different scenarios? And what it would mean if the universe ever did stop expanding. When we ask whether the universe will ever stop expanding, we're really asking about the long-term balance of forces that shape everything. Will gravity, the cosmic glue that binds matter together, ever overcome dark energy's relentless push? Or has the universe already passed the point of no return? The answer depends on one key factor: the density and nature of energy in the universe. Cosmologists describe this balance using what's called the Friedmann equation, which relates the rate of expansion to the total energy content, including matter, radiation, and dark energy. If the total density is greater than a certain critical value, the universe's expansion could eventually halt. If it's equal to or below that value, expansion will continue forever. Modern measurements, especially from the Planck satellite, show that the universe's total energy density is astonishingly close to the critical value, but slightly below it. That means the universe is likely open, destined to expand forever. The only way expansion could stop is if dark energy somehow weakens dramatically over time or reverses its effect. Let's imagine three possible futures. In the first, dark energy remains constant. The cosmological constant scenario. Expansion continues indefinitely, and galaxies move farther apart faster and faster. Over trillions of years, all galaxies outside our local group will disappear from view, their light stretched beyond detectability. The cosmos would become increasingly cold, empty, and quiet. This is known as the Big Freeze or heat death scenario. In the second, dark energy gradually fades. If its strength diminishes enough, gravity could eventually begin to slow expansion. In this case, the universe might coast for billions of years, then stop expanding entirely. After that, it could remain static for a time before collapsing inward in a big crunch where everything converges again. Though once considered possible, current data show little evidence that dark energy is weakening. In the third scenario, dark energy grows stronger with time. If its repulsive power increases faster than space can expand, it could tear apart everything. First galaxy clusters, then galaxies, then solar systems, and finally atoms themselves. This hypothetical ending is called the Big Rip. According to some models, if this were the true nature of dark energy, the universe could end tens of billions of years from now in a violent disintegration of space-time itself. So far, every observation suggests that the first outcome, eternal expansion, is the most likely. The universe's acceleration appears consistent and stable, with no sign of slowing or reversal. But the truth is, our data cover only a tiny fraction of cosmic history. The universe has existed for 13.8 billion years, and dark energy has dominated only for the last few billion. Predicting its long-term behavior from such a small window is like guessing the entire life of a star after watching a single flicker of light. To know if expansion could ever stop, we must understand what dark energy truly is. If it's an unchanging property of spacetime, then the expansion will continue forever. If it's a field that evolves, then perhaps, in some far-off epoch, it could shift or decay, changing the cosmic balance. There's even a remote possibility that the vacuum energy could flip sign, turning from repulsive to attractive, triggering a future collapse. But for now, the evidence is clear. The universe is expanding, and that expansion is accelerating. The galaxies are drifting farther apart. The cosmic background radiation is cooling, and the average density of matter is thinning with every passing second. Even if expansion were to stop one day, that moment would lie unimaginably far in the future, long after all stars have burned out and the cosmos has gone dark. Still, the question remains profound. To wonder whether the universe will stop expanding is to ask whether time itself could have an endpoint, whether the cosmic story, written in the language of physics, will one day close its final chapter. In the next part, we'll look more closely at each possible fate of the universe, exploring in detail how the Big Freeze, Big Crunch, and Big Rip would unfold. and what each one would mean for the structure of space, time, and matter itself. The universe's future can be imagined in 3 grand scenarios, each one determined by the strength of gravity, the power of dark energy, and the ultimate behavior of space itself. These are not fantasies. They are physical possibilities, built from equations, data, and the observed laws of nature. Together, they describe every way the story of the cosmos might end. Let's begin with the most widely accepted outcome: the Big Freeze, also known as the heat death of the universe. In this scenario, the expansion never stops. Space continues to stretch, and galaxies drift farther apart at ever-increasing speeds. Over billions of years, the distances between clusters grow so large that light from one can no longer reach another. Eventually, each surviving galaxy becomes an isolated island of stars in a vast cosmic ocean. Inside these galaxies, star formation slowly declines. Gas and dust, the fuel for new stars, are used up or blown away. Existing stars burn through their nuclear fuel, with the brightest and most massive dying first. The smaller, cooler stars live longer, glowing faintly for trillions of years before fading into black dwarfs, dense, dark remnants of their former brilliance. The second possibility is the Big Crunch, the reverse of the Big Bang. This could happen if the density of matter and dark energy were just right for gravity to overcome expansion. In such a case, the expansion would slow, halt, and then reverse. Galaxies would begin moving toward each other. Over billions of years, space would contract, heating everything as it shrinks. Stars and galaxies would collide. Temperatures and densities would rise until all matter and radiation merged into a single blazing point, a final singularity. The Big Crunch is poetic in a way, the universe returning to where it began, time folding back upon itself. Some theories suggest that such a collapse might even trigger a new expansion, a new universe born from the ashes of the old. Yet, modern evidence argues strongly against this outcome. Observations show that dark energy dominates over gravity, making a future collapse extremely unlikely. The third and most dramatic scenario is the Big Rip. This would occur if dark energy's strength increases over time instead of staying constant. As its repulsive force grows, it would first overcome the gravity that binds galaxy clusters together, tearing them apart. Then it would separate galaxies themselves, followed by solar systems, stars, and finally, planets. In the final moments of the Big Rip, the acceleration would become infinite. Space would stretch faster than light can travel. Even atoms would disintegrate as the bonds between particles fail. The universe would end not in fire or silence, but in pure fragmentation, every point in space becoming isolated from every other. Which of these fates will occur depends entirely on the nature of dark energy. If it remains constant, the Big Freeze is inevitable. If it fades, the Big Crunch could return as a possibility. If it strengthens, the Big Rip awaits. For now, all measurements point to the first, a slow, eternal expansion toward darkness and stillness. These cosmic outcomes are not just endings, they are reflections of the laws that govern everything. They tell us how energy, matter, and space-time themselves behave on the grandest scale imaginable. Each future, whether frozen, crushed, or torn apart, represents a different balance between creation and decay. As we study distant galaxies in the ancient light of the cosmic background, we are not just looking into the past, we are glimpsing potential futures. Every photon that reaches our telescopes carries not only the memory of what once was, but also the promise of what might be. In the next part, we'll look more closely at the Big Freeze, the most probable destiny of our universe, and what the cosmos will look like in the unimaginable eras that lie ahead. If the universe continues expanding forever, as current evidence suggests, its fate will be not fire or collapse, but gradual stillness. This slow, inevitable decline into silence is called the Big Freeze. It is a future where time stretches endlessly, galaxies drift apart, stars fade, and even the smallest particles lose their warmth to the cold fabric of space. To imagine this future, we must first picture what is happening now. The universe today is filled with light. The glow of countless stars and galaxies, the faint radiation from the Big Bang, and the energy of supernovae, quasars, and cosmic collisions. But all of that light has one thing in common. It is being stretched. As the universe expands, wavelengths grow longer, light becomes redder, and its energy weakens. The same process that carries galaxies apart also slowly drains the brightness from the cosmos. Over the next trillions of years, this expansion will reshape everything. Star formation will decline as the raw material, hydrogen gas, is used up or expelled from galaxies. The last bright stars will burn out, leaving behind a population of long-lived red dwarfs. These faint, cool stars can glow for up to 10 trillion years, far longer than the universe has existed so far. But even their light will one day fade. When the final stars exhaust their fuel, galaxies will no longer shine. They will be filled with dark remnants, white dwarfs, neutron stars, and black holes. Occasionally, a rare collision or merger will produce a brief flash of light, but these events will become increasingly infrequent as time passes and distances grow. In this distant era, even atoms may decay. If proton decay is real, something predicted by some grand unified theories, then matter itself will eventually disintegrate. Every atom of hydrogen, oxygen, carbon, and iron will vanish, leaving only radiation. The universe will have reached a state of maximum entropy, complete thermodynamic equilibrium, where no work, no structure, no change is possible. Though this fate sounds bleak, it is also deeply peaceful. The Big Freeze is not destruction in the violent sense. It is the slow fading of all processes, the quiet settling of the universe into perfect balance. It is the ultimate expression of the second law of thermodynamics, entropy increasing until there is no more energy left to transform. For all practical purposes, the universe will stop evolving. Time will still pass, but with nothing left to change, it will lose its meaning. The cosmos will persist, vast, dark, and almost empty, but forever silent. And yet, even this ending carries a trace of beauty. Every atom, every photon, every galaxy that once existed contributed to this equilibrium. The light of the first stars, the heat of supernovae, and the radiation from our own sun all helped move the universe toward this calm. The Big Freeze is not a tragedy. It is the conclusion of a grand and natural process that began with the Big Bang. In the next part, we'll turn to a more dramatic alternative, the Big Crunch, and see what would happen if the universe's expansion ever did stop in reverse, collapsing everything back to a single blinding point. Among all the theories about the universe's fate, the Big Crunch remains one of the most haunting and symmetrical. It imagines a cosmos that began with a bang and will end with one. In this scenario, expansion doesn't last forever. Instead, it gradually slows, halts, and reverses as gravity overcomes the outward motion of space itself. The entire universe, once vast and scattered, begins to fall inward toward a final, fiery collapse. To understand how such an end might happen, imagine the universe as a giant pendulum. The Big Bang is the moment of release, when everything swings outward. Expansion carries galaxies away from one another, stretching space itself. But gravity the great attractor, constantly works against it, pulling matter back inward. If the total mass and energy in the universe were great enough, gravity would eventually win, slowing the expansion until one day it stopped completely. At that precise moment, the universe would reach its maximum size. Galaxies would hang motionless in the expanding fabric of space, the outward momentum balanced exactly by gravity's pull. But this balance could not last. With no more outward energy to resist it, gravity would begin to pull everything back together. The pendulum would swing in the opposite direction. As the universe contracted, galaxies would begin to move toward one another. Over billions of years, the night sky would grow brighter as the cosmic distances shrank. Galaxy clusters would collide, merge, and ignite bursts of star formation. Temperatures everywhere would rise as matter became more densely packed. Eventually, even the large-scale structure of the cosmos, the vast web of filaments and voids, would dissolve. Galaxies would lose their identities, their stars scattering and interacting violently. Supermassive black holes at the centers of galaxies might merge, releasing colossal amounts of energy. The universe, once cold and dark, would grow hot again, filled with radiation. As contraction continued, space itself would begin to curve inward. Distances would shrink faster and faster, and time would appear to speed up. The temperature of the universe would rise to billions of degrees, just as it was in the first moments after the Big Bang. Eventually, matter would break down into its most fundamental components: protons, neutrons, and electrons. And then even those particles would dissolve into pure energy. In the final instance, everything, matter, radiation, and space, would collapse into a single, infinitely dense point. The universe would return to the state from which it began: a singularity. This is the Big Crunch, the reverse of creation, a mirror image of the Big Bang. Some theories suggest that this collapse might not be the end at all. Quantum effects could cause the singularity to rebound, triggering a new expansion, a big bounce, where a new universe is born from the old. If such cycles are real, the universe could have been expanding and contracting forever, an infinite rhythm of birth and rebirth across timeless ages. However, the Big Crunch depends on one condition: the total density of the universe must be high enough for gravity to overpower dark energy. Modern observations indicate the opposite. The universe's expansion is not slowing, it's accelerating. The density of matter is far too low to stop it. Even dark matter, which adds invisible mass, cannot provide enough gravitational pull. This means that the Big Crunch is unlikely in our current universe. Still, the idea remains important, not only as a theoretical possibility, but as a reminder of how gravity and expansion are two sides of the same cosmic balance. The equations that describe a collapsing universe are the same ones that describe an expanding one, just moving in reverse. The Big Crunch offers something profound: the thought that endings and beginnings might not be separate, that creation and destruction could be part of one continuous process. Even if our own universe never collapses, somewhere, perhaps in another region of reality, such cycles may be happening endlessly. In the next part, we'll explore the most extreme and unpredictable ending of all: the Big Rip, a universe torn apart by its own accelerating expansion. Of all the possible endings the universe might face, the Big Rip is perhaps the most terrifying and awe-inspiring. It describes a cosmos that doesn't simply expand forever, but expands faster and faster until it literally tears itself apart. In this future, not even atoms, not even the fabric of space-time itself, can survive the unstoppable acceleration driven by dark energy. The Big Rip begins with something that's already happening: the accelerated expansion of the universe. Right now, dark energy is pushing galaxies away from one another at an increasing rate. In the Standard Model, This acceleration will continue indefinitely but gradually, never reaching a destructive level. However, if dark energy's strength grows over time, if its density increases instead of staying constant, then its influence could become catastrophic. Then the process continues on smaller scales. The galaxies themselves, including our Milky Way, will no longer be held together. Stars that once orbited peacefully in the spiral arms will drift away into the void. Even before the universe ends, the night sky would grow increasingly empty as galaxies vanish beyond the cosmic horizon, their lights stretch to invisibility. Next, dark energy attacks the structure of solar systems. The gravitational bond between stars and their planets can no longer resist the accelerating expansion. Planets are torn from their orbits, drifting away as space between them stretches faster than gravity can pull them back. Finally, the destruction reaches the atomic scale. The bonds that hold stars together, the nuclear forces that hold atoms intact, and even the electromagnetic forces that bind electrons to their nuclei all fail. In the last moments, every molecule, every atom, every particle of matter is ripped apart. The universe ceases to have structure of any kind. If dark energy's strength continues to rise, the final moment, the literal tearing of space-time, would arrive after about 20 to 30 billion years from now, according to some models. Long before that, galaxies would vanish from sight, then stars, then planets. A few minutes before the end, atoms themselves would disintegrate. Finally, at the moment of the Big Rip, even the metric of space-time, the framework that defines distance and time, would diverge to infinity. This scenario is extreme, but it isn't purely science fiction. Observations from the Planck satellite, the Sloan Digital Sky Survey, and supernova data all suggest that W is very close to 1, though we cannot yet rule out values slightly below it. If it is even a little less, the Big Rip could one day happen. The idea is unsettling, but also fascinating. It reminds us that the universe is not a static thing. It's dynamic, evolving, alive in its own way. The same force that allowed galaxies to form may, in the far future, unmake them. Creation and destruction, expansion and collapse, all are part of the same cosmic balance. The Big Rip would mark a violent and final end to time as we know it. But even this extreme scenario may not be the last word. Some physicists believe that if the universe is torn apart completely, quantum effects could give rise to a new Big Bang, a rebirth from the wreckage of the old. Whether that's true or not, the Big Rip stands as a reminder of the universe's vast power and unpredictability. The same equations that describe its peaceful expansion also contain the possibility of its ultimate disintegration. In the next part, we'll look more closely at how physicists use equations and energy densities to predict these outcomes. The precise mathematics that tells us whether the universe will expand forever, collapse, or tear apart. When we talk about the universe expanding, it's natural to imagine it growing outward into something, like a balloon inflating into the air around it. But that picture, though helpful, isn't quite accurate. The universe doesn't expand into anything. Space itself stretches, carrying galaxies with it. The shape of that stretching, its curvature, determines how the universe behaves, how light travels, and whether expansion might ever stop. The concept of curvature comes directly from Einstein's general relativity. According to this theory, space can be curved by mass and energy. Just as a heavy object bends a rubber sheet, the mass of the entire universe bends the fabric of spacetime. Depending on how much total energy density the cosmos contains, space can have one of three geometries: closed, flat, or open. A closed universe has positive curvature. It bends like the surface of a sphere. If you could travel far enough in one direction, you would eventually return to where you started, just as a person walking around Earth ends up back at the same spot. In a closed universe, gravity is strong enough to eventually stop expansion, leading to a big crunch. A flat universe has zero curvature. Its geometry follows the familiar rules of Euclidean space. Parallel lines never meet, and the angles of a triangle always add up to 180 degrees. A flat universe expands forever, but slows gradually, approaching a constant rate in the distant future. An open universe has negative curvature. It bends outward like the shape of a saddle. In this case, space expands forever and faster than in the flat scenario. The geometry ensures that even distant light beams, which begin parallel, will diverge over time. So, what kind of universe do we live in? The answer comes from one of the most precise observations in the history of science. The cosmic microwave background, CMB. This ancient radiation, the afterglow of the Big Bang, carries imprints of the universe's geometry from when it was only 380,000 years old. By mapping tiny fluctuations in the CMB across the sky, satellites such as UMAP and Planck have measured the curvature of space with extraordinary accuracy. Their results show that the universe is flat to within a margin of 0.4%. In other words, if space is curved at all, its curvature is so slight that the observable universe, the region we can see, appears perfectly flat. This means the total energy density is almost exactly equal to the critical density required to balance expansion and gravity. However, flat does not necessarily mean infinite, though it could be. It means that on the largest scales, space behaves as though it has no measurable curvature. The universe might still be finite but unbounded, like the surface of a sphere in 3 dimensions extended into higher ones. If it is truly infinite, then the expansion we observe happens everywhere, simultaneously, with no center and no edge. This flatness raises a profound question. Why is the universe so precisely balanced? Small differences in the early universe could have made it highly curved today, either collapsing quickly or expanding too fast for galaxies to form. The solution may lie in the theory of cosmic inflation, the brief period of exponential expansion that occurred a fraction of a second after the Big Bang. Inflation would have smoothed and flattened the universe, explaining the near-perfect geometry we see today. Because of this flat geometry, light travels in straight paths across billions of light years. When we look deep into space, we are effectively looking through time, seeing the universe as it was billions of years ago. The flatness ensures that distant galaxies remain visible longer, their light not distorted by strong curvature. It's one reason we can observe such a vast cosmic horizon. Even in a flat universe, expansion continues, driven by dark energy. Flatness doesn't prevent acceleration. It only describes the shape of space, not the fate of time. What determines the end is the balance of energy within that flat framework. If dark energy remains constant, expansion will never stop. The universe will stay flat, but its contents will thin out forever. The geometry of space is one of the universe's most elegant truths. A perfect balance between the outward thrust of the Big Bang and the inward pull of gravity. We live in a cosmos where the scales of existence were set with exquisite precision, a place neither collapsing nor wildly exploding, but finely tuned for structure, life, and thought to emerge. In the next part, we'll turn from geometry to time, exploring how cosmic expansion affects the flow of time itself, and whether, in an ever-expanding universe, time could one day come to an end. When we talk about the universe expanding, we often think in terms of space, galaxies moving apart, distances increasing, light stretching. But expansion doesn't just affect space, it also shapes time itself. From the instant of the Big Bang until today, the flow of time has changed as the universe has evolved. To understand when or whether expansion could ever stop, we must also understand how time behaves in a universe that never stands still. In Einstein's theory of relativity, space and time are inseparable. They form a single entity called spacetime. The expansion of one affects the other. When space stretches, time also dilates in subtle but measurable ways. The rate at which clocks tick, the way light moves, and even how we define the present depend on the universe's expansion. Early in the universe's history, time flowed differently. When the cosmos was dense and hot, dominated by radiation, the gravitational field was intense. According to general relativity, stronger gravity slows down the passage of time relative to regions with weaker gravity. This means that during the first moments after the Big Bang, time advanced far more slowly compared to the way we experience it today. In a sense, the early universe was young in distance but ancient in energy. As the universe expanded and cooled, the density of matter and radiation decreased. Gravity weakened, and time began to flow more uniformly. Cosmic expansion didn't simply create more space. It allowed time to stretch along with it. This stretching is not something we notice locally, because our clocks, our atoms, and our perception all expand with the same rhythm. But across billions of light years, the difference becomes profound. Light traveling through expanding space experiences this stretching directly. Each wave of light emitted by a distant galaxy has been lengthened by the growth of the universe, a process called cosmological redshift. The more space has expanded since that light was emitted, the more its wavelength has stretched, and the more time has passed for the universe as a whole. The expansion of time also affects how we observe distant events. When we look at a galaxy billions of light years away, we are not just seeing it in space. We are seeing it as it existed billions of years ago. Because light takes time to travel, the farther we look, the further back in time we see. The universe therefore functions like a vast time machine, allowing us to watch its own history unfold in slow motion. The relationship between expansion and time goes deeper still. As space stretches faster, time between cosmic events, such as the formation of galaxies or the collisions of black holes, also lengthens. The universe's accelerated expansion means that processes that once took millions of years may now take billions. The cosmic clock, in a sense, is slowing down on the largest scales. If the universe keeps accelerating, this trend will continue. Galaxies will slip beyond the cosmic event horizon, the boundary beyond which light can never reach us. From our perspective, those galaxies will seem to freeze in time, their light redshifted until it fades away. Beyond that horizon, events will still occur, but their information will never reach us. The observable universe will effectively stop growing, not because expansion ends, but because time and distance stretch beyond our reach. This cosmic horizon defines what we can ever know. It's not a physical edge, but a limit imposed by the combined effects of space expansion and the finite speed of light. Even now, many galaxies exist whose light will never reach us, because space between us and them expands faster than light can bridge the gap. In an accelerating universe, that boundary grows closer over time. The more expansion accelerates, the more isolated our region of space becomes. In a far future dominated entirely by dark energy, the flow of cosmic time may slow almost to stillness. The universe will continue to expand, but with no new events to mark its passage. In such a reality, time will lose its meaning, not because it stops, but because nothing remains to measure it. A universe without change is a universe without time. This perspective reminds us that time is not separate from the cosmos. It is part of its structure. When we say the universe expands, we are saying that space-time itself is evolving. The stage of existence is growing, and so is the script of history written upon it. In the next part, We'll explore how expansion affects light and horizons, how the stretching of space defines what we can see, what we can never see, and what that means for the ultimate question: when will expansion stop, if ever? The more we learn about the expanding universe, the clearer it becomes that there are limits to what we can ever see or know. Light, the messenger of the cosmos, travels at a finite speed, yet space itself is not bound by that limit. It can expand faster than light can cross it. This simple fact creates a boundary between what is visible and what is forever hidden, the cosmic horizon. There are actually several types of horizons in cosmology, but two are especially important: the particle horizon and the event horizon. The particle horizon represents the farthest distance light has been able to travel since the Big Bang. It marks the edge of the observable universe, the boundary of what we can currently see. Beyond it, there may be countless galaxies, but their light has not had enough time to reach us, even after 13.8 billion years. However, as the universe continues to expand, another boundary forms: the event horizon. This one is even more fundamental. It defines the limit beyond which events occurring today will never be observable in the future, no matter how long we wait. This happens because the space between us and those regions is expanding faster than light can traverse it. Even if a galaxy emitted light now, that light would never bridge the growing distance. This means that while the observable universe has a finite size, about 93 billion light-years across, the total universe could be vastly larger, perhaps even infinite. We can only ever observe a small bubble of reality, one that expands slowly as more light from distant regions finally reaches us. But at the same time, the event horizon defines an ultimate limit. Regions beyond it are lost to us forever. As cosmic expansion accelerates, more and more galaxies cross that event horizon. Every second, space stretches just a little faster, carrying distant galaxies away beyond the speed of light. We cannot chase them, we cannot communicate with them, and one day their light will fade completely. The farther into the future we go, the emptier the sky will become. In roughly 100 billion years, observers in the Milky Way, or whatever remains of it after merging with Andromeda, will see only the few galaxies of our local group. Everything else, billions of galaxies that fill the sky today, will have disappeared beyond the cosmic horizon. The universe will seem smaller, even though it is expanding faster than ever. This cosmic isolation has deep implications. The universe will become increasingly homogeneous and featureless. Future astronomers, if any exist, will have no observational evidence that an expansion ever occurred. The cosmic microwave background will fade, redshifted beyond detectability. The evidence of the Big Bang itself will vanish into invisibility. The universe will seem static once again, a strange echo of how humans once saw it before Hubble's discovery. This horizon effect also defines how we experience cosmic time. Because of expansion, there is a maximum distance from which information can reach us, and that distance grows smaller in an accelerating universe. The more rapidly space expands, the less of it we can interact with. In this way, cosmic acceleration effectively creates a shrinking, observable domain inside an infinitely growing reality. To visualize it, imagine dots on an inflating balloon. Each dot represents a galaxy. As the balloon inflates, the distance between dots increases. If the balloon inflates fast enough, some dots move apart faster than light. From any one dot's perspective, those others fade away. The surface itself, the fabric of space, continues to expand everywhere, but each observer's visible region becomes an isolated island of light surrounded by unreachable darkness. This isolation will deepen as time goes on. The radiation that fills the universe will cool. The background glow will fade into wavelengths longer than any detectable signal. Eventually, the universe will become a silent expanse, not because it ends, but because its speed of expansion makes communication across it impossible. In an accelerating cosmos, the event horizon is not just a boundary of vision. It is a boundary of causality. Beyond it, events no longer have any influence on us. They exist, but they are forever disconnected from our timeline. This makes the universe, on the grandest scale, a collection of isolated regions, countless island universes, expanding separately into eternity. This concept forces us to rethink what it means to ask when expansion might stop. From within our horizon, expansion will never appear to halt. Beyond it, regions we can't see may already behave differently, but we will never know. Expansion doesn't just separate galaxies, it separates realities. In the next part, we'll look at how scientists use these horizons and cosmic boundaries to measure the universe's age, size, and fate, and what those measurements tell us about whether expansion could ever truly come to an end. If we want to know when the universe might stop expanding, we first have to understand how we measure that expansion, and even more remarkably, how we can measure something as immense and intangible as the universe itself. The cosmos is not a laboratory experiment. We cannot step outside of it or repeat it. Instead, we must rely on light, geometry, and time, the few tools the universe allows us to use. The key to everything is light. Every photon that reaches us carries information about its journey, how far it traveled, how long it traveled, and how the space through which it moved has stretched. By measuring these changes, scientists can reconstruct the history of expansion with astonishing precision. The first step is to determine distances. In astronomy, distance cannot be measured directly. There is no ruler long enough. Instead, scientists use standard candles, objects whose intrinsic brightness is known. The best examples are Cepheid variable stars and Type Ia supernovae. Cepheids pulse at regular intervals, and the period of their pulsation reveals their true luminosity. Type Ia supernovae always explode with roughly the same brightness. By comparing how bright they appear from Earth to how bright they truly are, astronomers can calculate their distance. Once the distance is known, the redshift of the object's light reveals how much the universe has expanded during the time that light has been traveling. Combining these two quantities, distance and redshift, allows scientists to measure the rate of expansion, known as the Hubble constant. Modern values of the Hubble constant lie between 67 and 74 kilometers per second per megaparsec, meaning that for every 3.26 million light-years of distance, galaxies move away from us 67 to 74 kilometers per second faster. The range may seem small, but the debate around it, known as the Hubble tension, has profound implications. If the expansion rate is on the higher end, the universe is slightly younger and its acceleration stronger. If it's lower, the universe is older and its expansion more gradual. Other measurements come from the cosmic microwave background, CMB, the faint afterglow of the Big Bang. This ancient light has traveled for 13.8 billion years, carrying a frozen imprint of the early universe's density, temperature, and geometry. By mapping the tiny fluctuations in the CMB, satellites like Planck and WMAP have given us precise values for the age, composition, and shape of the cosmos. By combining CMB data with measurements of galaxy distribution and supernova distances, cosmologists can construct a detailed timeline of expansion. The universe spent its first few billion years slowing down under the influence of gravity, then began accelerating about 5 billion years ago when dark energy became dominant. The point at which that shift occurred, the so-called cosmic acceleration transition, is one of the clearest indicators that the expansion will not stop anytime soon. The size of the universe is even harder to define. The observable universe, the part we can see, extends roughly 46.5 billion light-years in every direction. But because the universe has been expanding while light was traveling toward us, The true distance to those regions today is much greater than 13.8 billion light-years. Beyond that horizon, we have no direct access. The total universe could be hundreds of times larger, possibly infinite. From these observations, scientists can estimate the total density of energy and matter, which determines the universe's fate. As of now, about 68% of it is dark energy, 27% dark matter, and only 5% normal matter. With dark energy so dominant, expansion will not slow, it will accelerate forever. The ability to extract this knowledge from faint patterns of light is one of humanity's greatest achievements. Every telescope, every detector, and every equation extends our reach deeper into time. The more precisely we measure, the more clearly we see the universe's story, not just its past, but its potential futures. In the next part, we'll explore why the expansion began in the first place, what the Big Bang really was, how inflation started it all, and whether the same mechanism could ever bring it to an end. If the universe never stops expanding, then time itself stretches into infinity. Every galaxy that drifts away, every fading star, every photon that loses its last trace of light becomes part of a story that never truly ends. It's a story written not in words or images, but in motion, in the simple act of space continuing to grow. Cosmic expansion is not a force that pushes outward. It is the fabric of reality changing shape. From the first instant of the Big Bang, expansion has defined everything that exists. Not only where matter moves, but how time flows, how light travels, and even how life can arise. Without expansion, there would be no cooling, no galaxies, no stars, no chemistry, and no us. The fact that we can look into the night sky and see billions of galaxies means that expansion has been perfectly balanced, not too fast to prevent structure, not too slow to cause collapse. The story of the universe is, in a sense, the story of balance gradually being lost. Gravity once pulled strongly enough to gather matter into stars and galaxies, but as the universe thinned, its strength waned. Dark energy, faint, steady, and everywhere, took control. Now expansion accelerates, and the universe slides slowly toward isolation. It is not destruction, but diffusion, a spreading of everything that once was bright and dense into a smooth, eternal calm. And yet, within that calm, lies something profound. Even as the universe grows emptier, it never stops existing. Space itself endures. Time continues. The laws of physics remain. The echoes of all that ever happened, the formation of galaxies, the birth of stars, the emergence of life, are woven into the structure of space-time forever. Perhaps the universe does not seek an ending. Perhaps it only transforms, endlessly shifting between states of energy and stillness, light and darkness, birth and decay. The expansion that began nearly 14 billion years ago may be only one verse in a poem without end, a cosmic rhythm that pulses across eternity. We too are part of that rhythm. Every atom in our bodies was forged in stars that existed billions of years ago, scattered across the universe by supernovae, gathered again into new worlds. We are the product of expansion, the living awareness of a cosmos that became complex enough to observe itself. When we look into the night sky, we are not seeing something distant. We are seeing our own origin, stretched across time. If the universe expands forever, then every thought, every spark of consciousness, every particle that has ever existed will remain part of that expansion. The light that leaves your eyes when you gaze at a star will travel endlessly through space, red shifting forever, but never truly vanishing. Nothing in the universe is ever lost completely. It only changes form, following the same quiet law that has guided everything since the beginning. One day, far beyond our own time, all light will fade. But even then, the structure of space-time will still carry the memory of what once was. The energy that filled the stars, the motion of galaxies, the whisper of life, all of it becomes part of the universe's endless unfolding. So perhaps the answer to the question, when will the universe stop expanding, is simple: never. Because expansion is not something the universe does. It is what the universe is. The act of being itself is expansion. The continual stretching of existence, the infinite deepening of time. And in that truth lies something quietly beautiful. The universe does not race toward an ending. It drifts toward stillness, not in despair, but in peace. The stars we see tonight are temporary, but the space between them, the silent canvas on which they shine, will endure forever. The universe began in light. It will end in calm. And between those two infinities, the flash of beginning and the breath of eternity, there is us, a brief consciousness aware of it all, watching the expansion, listening to the quiet rhythm of the cosmos, and realizing that even silence can be eternal.